So on Friday, we looked at satellite motion. We defined a satellite as an object that revolves around something else. Specifically, in the context of this unit, a satellite will be something that revolves around something else because of gravity. It doesn't have to be, but usually it is because of gravity, and certainly in this unit, that's what we're going to be talking about. Satellites that are orbiting because of gravity. We got two kinds of those satellites, right? One's an artificial satellite, one's a natural satellite. Example of an artificial satellite might be what? The space station, the International Space Station. An example of a natural satellite might be what? The moon orbiting around the Earth. Be careful, if I ask you that on a test, don't just say the moon. I know exactly what you meant there, but don't just say the moon. Because if you're talking about the moon in the context of the sun, then the moon's not a satellite, right? But if you're talking about the moon in the context of the Earth, it is, because it's orbiting around the Earth. Absolutely. Yeah, the Earth around the sun is a good example of a natural satellite as well. So anything that orbits something else, including the Earth orbiting around the sun, including the moon orbiting around the Earth, including the space station orbiting around the Earth as well. So when we analyze these objects that are revolving around something else, we got to remember that because they're going in a circle, they experience a centripetal force. But remember, back when we started this unit, we said that a centripetal force is never a fundamental force. It's always caused by something else. In the case of the car going around the turn, it's caused by friction. In the case of the keys going around my head, it was caused by my hand. In the case of your lab that you handed in last week, which, by the way, you have handed back to you now, in the case of the lab where I was swinging that rubber stopper around through that PVC tubing, the centripetal force was caused by the hanging mass. The centripetal force has got to be always caused by something. When we're talking about a satellite, it's going to be caused by gravity. So let's set those two equal to each other. Centripetal force equal to gravity. The centripetal force is mv squared over r. Gravity is gm1 m2 over r squared. Now, we talked about this last week a couple of times. When do we use gm1 m2 over r squared for gravity? When do we use m times g for gravity? Well, they're both always valid. But the problem with this force of gravity, sometimes at least, is what? This one is always valid, so is this one. This one tends to be a little bit more versatile because it doesn't depend upon this. We don't always know the number for G. Right? It's 9.81 on the surface of the Earth, but if we're talking about somewhere out there 400 kilometers above the surface of the Earth where the space station orbits, we don't know what little g is. If you know what little g is, you can use this, m times g, instead of gm1 m2 over r squared. It becomes a little bit simpler, right? If you know the value of little g. Yeah, go ahead.
Well, I know the number for gravity on Earth is 9.8.
Yep. So the question is, we know that that g on Earth is 9.81 meters per second squared, or 9.81 newtons per kilogram, we could say. What does that number represent? It is, we called it up until last week, we called it the gravitational acceleration, the acceleration due to gravity. So if I put something in that 9.81, it will accelerate at 9.81 meters per second squared. But we now also know it as the gravitational field strength. So it's the strength of the influence of the Earth, whether or not there's something there to experience it. So up until last week, we would have said, okay, you put the pen in the field, it's going to accelerate downward at 9.81 meters per second squared. But now we know that we're going to say the field strength is 9.81, whether or not the pen accelerates downward or not, even if there's nothing there. We know it's the influence of the Earth, whether or not there's anything there to be influenced. Okay, but in the end, if you put something there, it will accelerate at that rate, 9.81 meters per second squared. On the surface of the Earth, right? Anywhere else, it's going to be a different value. All right, so we got to start canceling some things out to make this a little bit simpler now. We can cancel out one of the masses, but which mass do we cancel out? Well, we're going to say that the Mass 1, we're going to say is the mass of the satellite. This would be the mass of the producer, probably the mass of the Earth in most cases. This is going to be the mass of the satellite as well that's orbiting around something else. So we cancel out MS. We can also cancel out one of the R's because it appears in both terms. We're left now with V squared, speed of the satellite squared, is equal to G times the mass of the producer over R. Not R squared because we canceled out one of the R's, just R. You want to find speed? Square root it. You want to find R? Rearrange to solve for R. Want to find M? Same deal. Rearrange to solve for M. We had 2 questions for homework last night that involved this. Question 1 and 2 on page 278. Any issues with either of those questions on page 278? No? Number 2? The moon Miranda orbits Uranus at a speed of 6.68 times 10 to the 3 meters per second. So 6,600 meters per second. Like 20 times the speed of sound about. Use this speed and the mass of Uranus to determine the radius of Miranda's orbit. And you get the mass of the planet here as well. The mass of the central body, we'll call it. The mass of the object that's being revolved around. Okay, clearly this moon is a satellite. So we're going to say the centripetal force is equal to the gravitational force. Every time you see a satellite problem, this is what you're going to do. And you are going to see a satellite problem on your Thursday's test. Do this. FC equals FG. We're going to set MV squared over R equal to GM1 M2 over R squared. Cancel one of the R's, cancel one of the M's. We're left with V squared is equal to G times the mass of the producer, which would be Uranus here, divided by R. We want to find the radius here. Okay, the radius of the orbit of this moon. So let's take the R up by multiplying and the V squared by dividing. G times the mass of the producer over V squared. G is 6.67 times 10 to the minus 11 times the mass of the planet, which is 8.68 times 10 to the 25, divided by V squared. Make sure you use some brackets on the bottom. You got to square that, but because we have an exponent on the number already, it's helpful to use some brackets there. We're doing our math there. Should work out, I assume, to be 1.30 times 10 to the 8. Kenzie, question? Why do we cancel out the mass of the experiencer, not the producer? Good question. Okay, we'll go through that. We talked about that before, but we'll go through it again because that's an important fact there. Let's make a new page there. If we derive the equation, and really we should derive the equation every time because the equation that we get out of this doesn't appear on your data sheet. This part of it does. This part of it does. But the combined equation doesn't. Now, why do we cancel out the mass of the experiencer? Well, first of all, Mackenzie, let's get our terms straight here. Not that your term is wrong, but just that we're going by the same language here. The experiencer here, we're going to say is the thing that's doing the orbiting. So in this case of the last question, it would be the mass of the moon, right? One of these masses right here is going to be the mass of the satellite or the experiencer. One of them is going to be the mass of the planet or the producer. Does that make sense? So Gm1 M2 over R squared. Now, what mass do we have over here for the centripetal force? We're talking about the force that's acting on the object that's doing the revolving. Then we're talking about the mass of the object that's doing the revolving. So we'll call that MS, or using your terminology, it would be ME, the mass of the experiencer. Either way, the mass of that satellite slash experiencer cancels, and we're left with the mass of the producer only. That make sense? And then, of course, R's cancel because there's only one kind of R there. Is that okay for everyone? Plug those numbers into your calculator. Make sure you can get that number because this is one where we should be able to do it. But sometimes when we go to plug the numbers in, sometimes it just doesn't work out for us because we're having a little bit of trouble with the data entry on that. Okay, brackets on the bottom, square it, and so on. If you can't get that, let me know and I'll help you out with it. Yep. Yep. That's a good question. And it's funny that nobody else has asked that question yet because it's a good question. We talked about Kepler's laws last week, right? The first one is the law of elliptical orbits. Let's have a look now at one more example for us. Oh, sorry, yeah, the elliptical orbit question before we paused it there, which is a good question. Funny that nobody else had asked that question. Last week we talked about the law of the elliptical orbits, Kepler's first law, right? We said that planets revolve around the sun in elliptical paths. Presumably moons orbit planets in elliptical paths as well. The radius changes. So what do we do in that context? Well, we're assuming it's a circle, which isn't quite true, right? But remember the diagram of the elliptical orbit that we drew last week? We said it was much exaggerated, was much closer to a circle than what we were actually showing. That means that setting FC equal to FG, although it's an approximation, it's a good approximation. The radius doesn't change that much. But understand, when we do use an R value there, understand that it is an average radius. It's not necessarily the exact radius at any given moment. It's the average radius. It just doesn't change all that much because although it is an ellipse, it's close to being a circle. Okay? All right. 5.12 on page 279 says, Landsat is an Earth imaging satellite that takes pictures of the Earth's ozone layer and geological features. It orbits Earth at a height of 912 kilometers. You see the picture there. Okay, 912 kilometers above the surface of the Earth, which is about 2.5 times the orbit of the space shuttle, or the space station, I should say, about 400 kilometers up. What's the orbital period and the orbital speed? Clearly, it's a satellite, so we're going to say FC equals FG because that's what we do when we have satellites. MV squared over R is equal to G M1 M2 over R squared. We're going to cancel out one of the M's, one of the R's. We're left with V squared equal to G times the mass of the producer, which is going to be the mass of the Earth, over R squared. We're looking for speed and period, but let's find speed first. That's easier. Then we'll deal with the period after that. V is equal to the square root of G times the mass of the producer over R. It's the value of G, 6.67 times 10 to the minus 11. Always is. The mass of the producer, we're talking about the Earth here, right? Not the satellite. We don't even know what the satellite weighs. You don't need to know. The mass of the Earth from our data sheet is 5.97 times 10 to the 27 kilograms. And the value of R, 912. Got to convert that to meters though, right? What's the value of R here? It's not 912. 912,000 converted to meters, but that's still not our value of R. Can we? Good. 912,000 meters plus the radius of the Earth, 6.38 times 10 to the 6. We want the distance from the satellite to the center of whatever's causing it to orbit around, in this case, the Earth. Now, good news is we don't have to square anything there. Bad news is we do have to square root. Let's do this one together on our calculator on the board here. We're going to say 6.67 times 10 to the minus 11 times 5.97 times 10 to the, I got 10 to the 2 there. It should be 10 to the 24. It's the mass of the Earth. 5.97 times 10 to the 24. Let's divide that by, now make sure, please make sure here you use brackets. Divide it by what's on the bottom, 912 plus 6.38 times 10 to the 6. Do you guys understand why I had to add those two numbers together? And I didn't have to in my last example, and I didn't have to on my practice problems that I did for homework. You got to add them because we're given the distance from the Earth's surface to the Earth's center, and then the distance above the Earth's surface. In the last question, we were just given the distance that we needed. And we didn't have to add them because we already had that value. We already had the sum of those values. All right, get this. That's not our answer, though. We got to square root that still. We end up getting 7389.7. Which is, we're going to round that to 3 digits, 7.39 times 10 to the 3 meters per second. I'm sorry? We're going to find the orbital period now, which is the easy part now, once we have the speed. Anybody have an idea? Question we just did was similar to what we did for homework, except that we had to add those two distances together. This is a bit different, but it's real similar to something we did the first day of this unit. What is it? Good. Thank you, Stephen. V is equal to 2 pi r divided by t. So we're going to say t now. 2 pi r divided by v. Remember the radius, the distance is going to be both of those numbers combined. Don't just blindly add two numbers together. Okay, understand why we add them together. Okay, we want the distance from the center of the planet to wherever the satellite is. If we're given two random numbers, we don't just add them. If we're given two numbers that add up to give me the distance from the satellite to the center of the Earth, then we add them together. Divide that by the speed, which we just found. Let's use the unrounded number, 7389.7. Now let's see what we get here. 2 times pi times, use some brackets here, 912,000 plus 6.38 times 10 to the 6. Let's divide that by the number that we just had, 7389. And we're going to get 543,243. What are my units there? What are my units there? Mackenzie, what are the units? Seconds, right. Now, the question didn't ask what's the period in seconds or hours or days or whatever. So we're going to leave it in seconds. Okay, if we had to convert this to minutes, we'd divide by 60. If we had to convert it to hours, we'd divide by 60 again, and so on. We are going to put this in scientific notation, though, so we can put it in the right number of digits. 5.43 times 10 to the 5 seconds. We good there? You got a different answer. Did I make a mistake? Or did Katie make a mistake? Katie, you know what? It's probably me, because I made a mistake once before. 1987. No, you know what? Actually, no, I'm lying. I also made one in 1993. That's two mistakes I made. So it could very well be me again. Katie, what did you end up getting? 6,200. Anybody else get that? Anybody else get my number? Anybody else get my number? You got my number? All right, well, let's try it again. Katie, do you have these numbers? These numbers all the same? Okay, so let's go through this process again. 2 times pi times, I'm sorry? Oh, yeah, it should be 6.38, right? Okay, so I did make a mistake there. Although that's not going to change the base. It's still going to be 5.43. It's just going to be times 10 to the something else. So 2 times pi times 912 plus 6.38 times 10 to the 6 divided by the speed, which is 7389.699. No, I don't get the same number. Oh yeah, right. No, because it's added to 912. Yeah. So it comes out to be 6,200. Is that what you got? Would you look at that, Katie? My first mistake of the new millennium. It's not even a new we've been here for 15 years. It's not even a new millennium, but 6.20 times 10 to the 3. Anybody else get that? Yeah, now the hands are going up. Yeah, now that you know that it's right, have some confidence. Challenge me. You think I made a mistake? Challenge me on it. Please do. Stand up for yourselves. Yeah.
What was your mistake in 1990?
I don't remember. It was so inconsequential, I don't remember. It was a small one. Good? Yep. Miles just asked a question, said, I want to find out if how long it takes to go around in hours. We've got seconds here. We want to find it out in hours, let's say. Although in this question, we didn't need to convert to hours, but let's say on a test I said find the number in hours. How would you do this? Well, the conversion factor is 3,600 because there's 3,600 seconds in an hour. Do we multiply or do we divide? You know what? Guess. I don't care, guess. But just check your answer to see if it's reasonable. If it takes 6,200 seconds and we're guessing that we're multiplying, I don't know what you get when you multiply those two numbers together, but it's going to be a really, really big value, right? You can't have more hours than seconds because an hour is a lot bigger, right? There's 24 hours in a day. There's like something like 86,000 seconds in a day. Hours is always smaller than seconds. So what are you going to do? You're not going to multiply by 3,600. You're going to divide by 3,600, right? Which is going to work out to be, I don't know, 1 point something hours, right? 1.72. Okay. Make sense, guys? All right, here's your homework. Page 279. Remember, this is a height of 359.2 kilometers above the Earth's surface. Remember, this altitude is 114,000 kilometers above the Earth's surface. What are you going to have to do with both of those numbers? Add what? Yeah, add the radius of the Earth to it to get that total distance, right? All right, that's your homework for tomorrow.